Hello, this is Brian Washburn. I'm going to do practice exam number 2. This is part 2, so I'm going to start with problem 3. Problem 3 looks like this. I have a potential that looks like U of R, a central potential that looks like beta times R cubed. Okay. First thing I'm going to do is sketch the effective potential. The effective potential is going to look like, so I add the potential associated with a centrifugal term, and so angular momentum will be conserved because everything is central, and so that's my effective potential there. I'm going to sketch that guy. So again, what I have is the 1 over r squared term kind of does this, okay, and then the beta cube term so a cubic function in general does something like that. So this guy is going to do something like that. And so then my effective potential looks like this. So I expect an equilibrium position. Okay, so that's part A. Part B says for what energy and angular momentum will the orbit be a circle of radius A about the origin? Well, you think about circles a closed shape whose radius doesn't change. Well, that must mean that this thing has a radius at the equilibrium position, which I'm going to call R naught, or this is R. This is U effective of R. Okay? So what I have to do is I have to find, use the notation I'm going to call it A. That's what the problem says. So I have to find that. Okay. So, and by the way, that also energy is going to be the minimum energy of the system, okay, for a bound orbit. So in that case, the total energy is going to be equal to U effective at R equals A. So that's the energy of that circle. And that's going to be equal to L squared 2ma squared plus beta times A cubed. Okay. Where the angular momentum of the system is going to be equal to L mass, the radius, which is A, times the angular speed. Okay. So that's what the energy is going to be. To find what it asks for, express the energy in terms and angular momentum only in terms of MB, MA, and beta. Okay, so here what I have is I have the angular momentum expressed. Okay. So now what I have to do is I have to find a relationship between L and A. So let's actually find A. The way I'm going to find A is I'm going to write my effective force from my effective potential is this going to be equal to, this is my centrifugal term, and then looking at the other term, realizing that the force is equal to minus the partial U respect to R, 3 beta R squared. And then I'm going to set F effective equal to 0 at R equal A, because that's my equilibrium position. I'm going to get 0 is going to be equal to L squared MA cubed minus 3 beta A squared. So I can then solve for A. What I can do is I can multiply. I want to solve for L, right? So L squared is going to be equal to, bringing this over to right, 3 beta A squared times MA cubed. And so L is going to be equal to, well, plus or minus, we'll take the plus case, of 3m beta a to the 5th square root. So that's what L is. And then part C asks, oh, by the way, so we don't have the energy yet, remember, so we have L. The next part asks for what's the, going to express the energy and angular momentum only in terms of M, A, and beta. So we have the angular momentum, now we have to get the energy. Let's finish up what we had before. Using this expression here, E is equal to L squared 2M squared plus beta A cubed. I'm going to stick in the result I have for L squared. That's going to give me 3M beta A to the 5th divided by 2MA squared plus beta cubed. That's going to give me 3 over 2 beta A to the 3rd plus beta A to the 3rd. And that's just going to equal to 5 halves beta A cubed. So that's the energy for a circular orbit. The final question, part C, asks what's the period of circular orbit? Okay. Well, before we had L, that's the angular momentum of the system, MA squared phi dot. We can solve for phi dot. Phi dot tells me the angular, that is the angular acceleration. Okay. So that's going to be L MA squared. Now we can stick in what we had from L before using the positive solution, 3M beta A squared square root MA squared. We can bring, I can bring this in. The rest is just stupid algebra. Not even algebra, it's just squared A fourth. Okay, simplifying things out, put that all under the square root sign. And then if I simplify things, I get phi dot is equal to 3 beta. Masses cancel out. No, they don't cancel out. There's a mass in the denominator. Sorry about that. Okay. So then how do I get the period? Well, that is the, in EP language, we'd call that the angular frequency. That's the rate of change, how many two pi's per second we go through. So then the period is just equal to 2 pi divided by omega. And so it's just 2 pi times M3 BA beta A. That's it. That's the period of the orbit. Okay. So finally, let's do problem number 4. Look at that. So in problem number 4, what we have is this tabletop problem. I have a mass that is on a table, and there is a spring, and this is in the XZ plane. However, the whole system can rotate using on a tabletop like this, X, Y, and then here I have a spring, and so it's naturally called this distance from the origin rho, and then this angle here as phi. So what I want to do here is I want to determine the Hamiltonian for the system. Okay. And then I'm going to identify any conserved quantities, and then we're going to look at a case when we tip the tabletop. Okay. So you can see that, okay, well, the kinetic energy, so there's a couple of ways to write the Hamiltonian. You could write the Lagrangian, or you could just say that, well, the Hamiltonian is going to equal to the kinetic energy plus potential energy. Let's just do that. So the Hamiltonian is going to be equal to T plus U. Okay. U is just the only potential that we're going to have is that of the spring. So that's going to be 1/2 K rho minus A. The system will be conservative. There's no non-conservative forces acting on it. So thus I can say the Hamiltonian is equal to the total mechanical energy. And then, okay, so then there is an angular momentum associated. There's an angular momentum associated with thing rotating, and then there's a linear momentum. So then I would say, well, again, my generalized coordinates are rho and phi, and in my Hamiltonian system, I'm going to have a piece of rho and a piece of phi. This is going to be the momentum associated with motion along the rho, so that's a real linear momentum. And this is the momentum or the angular momentum associated with rotating. So I could just sit down and write down the Hamiltonian. It's going to be, so basically there's going to be, well, actually let's write on the kinetic energy first. So the kinetic energy is going to be equal to, you can say that, well, there's two components of kinetic energy. One is associated with motion along rho, and then the kinetic energy of motion along phi. Okay, so the motion along rho is just going to be p sub rho squared over 2m. And then the kinetic energy associated with motion along phi is going to be p sub phi. That's an angular momentum. Instead of 2m, it's going to be 2I, the moment inertia, which is just this. So that's kinetic energy right there. Okay. Now you can look at my solutions. I actually did it the way I actually solved this in my solutions, which is not exactly what I did here. What I did was I actually used the transformation from, I got the Lagrangian first and got the transformation from there. But this is just as good. And then now the Hamiltonian is just going to be the sum of the two, so it's just going to be equal to that's kinetic energy plus potential energy. Okay, that's it. Okay, so then part B asks, identify any conserved quantities. Provide a physical explanation for why these quantities are conserved. Well, energy, mechanical energy is conserved because there's no non-conservative forces. The Hamiltonian is a function of rho, piece of rho, but piece of phi. It is cyclic in phi. That means the angular momentum associated with phi. Oh, did I say that wrong? Yeah, the angular momentum associated. So it's not a function, explicit function of phi, but it's a the angular momentum is going to be constant. Okay, so that, and the reason why it's constant is because if you think what forces act on the object. So if we just draw a free body diagram, so here's my origin. There's a spring acting like here. So what force is acting on? There's a normal force here, and then there's a spring force, and that's the spring force there. So the net force acting on the mass is not zero, but none of those forces create a torque, because remember, torque is equal to R across the net force. Well, R, in this case, let's see. Well, the normal force doesn't cause the thing to spin like this. It can't do that. And then the spring force is along R, so the cross product is zero. Oh, by the way, yeah, I'm an idiot. There's mg acting down too. So the net force in the y direction is equal to zero, so there's no net force in the y, and thus there's no torque in that direction. Okay. And then the force in the x direction, or minus x direction, that doesn't cause a torque. Okay. Now part C, take a look at part C. Now what we do in part C is instead we tilt the tabletop such like this. Okay, so actually this is let's just remind ourselves this is actually, this diagram is very important. When the table's flat, notice that the forces acting on F normal is in the same direction as mg, and thus gravity doesn't create a torque on the object, and also the spring force does not create a torque. So the net, so there's no forces that create a torque. Okay. Part C asks that now we tilt the table, provide a physical explanation for any quantities that become not conserved when you tilt the table. If you tilt the table, what happens there is, again, so let's just draw a free body diagram. My normal force points up like this. I have G, mg downward, and then the spring force again is along this direction here. And so this is my x direction and this is my y direction here. Okay. However, now the normal force is not the normal force. Mg is not totally equal to the normal force. They're not in the same directions. Okay, so there's a small component of the normal force in that direction right there. Well, that thing there is going to create a torque. Okay, that's going to create a torque. And so since it now creates a torque, P sub v, which was conserved when the table's flat, this is no longer going to be a constant. Okay. Mechanical energy still will be a constant, but P sub v will not be constant. The other way of explaining this is by using Noether's theorem. If I have the flat system, the flat tabletop, if I rotate the entire system like this, you couldn't tell. So the Lagrangian would be invariant under rotation. So thus, the Lagrangian is space isotropic. This guy here, if I took the whole system rotate like this, you could tell. Because now, instead of the table tilted, say I rotated it 180 degrees. Well, initially, the table looks like this. If I rotated 180 degrees, it would do this, and you could tell that. So the system is not isotropic anymore, and thus Lagrangian, thus angular momentum should not be conserved. Okay, so that's the problem. That's number 4. So we're kind of done here. Good luck with that, and we'll see you in class. Bye-bye.